We're now going to begin our overview of Java, focusing initially on key object-oriented concepts and features supported by the language. These concepts and features include abstraction, inheritance, and polymorphism. And although our focus in this material is on modern Java's functional programming features, understanding Java's object-oriented foundations is also important, if for no other reason that they're very pervasive in practice. Almost all programs you see that we'll cover that use modern Java features also leverage the object-oriented features one way or another. Java was originally designed just to be an object-oriented programming language. Therefore, it's no surprise it supports key object-oriented concepts and features, such as objects, classes, inheritance, interfaces, packages, and so on and so forth. We'll showcase these concepts and features via an example that defines a simplified hierarchy of set classes that are implemented using the set classes in the Java collection framework. And all these example code snippets we'll be taking a look at here in this particular part of the lecture are also available in open source form at the link at the bottom of the slide in the EX0 project. We'll start off by talking about data and control abstraction. Data abstraction is used to define well-defined application programming interfaces, or APIs. Well-defined APIs help to decouple interfaces from implementations in order to enhance reuse and modularity in software programs. Likewise, control abstraction helps to show programmers from low-level implementation details associated with various control constructs you'll find in Java, such as iteration, such as loops, switching, conditional expressions, and so on. For example, the simple abstract set class defines a foundational API for adding, searching, and iterating over a set abstraction. And it also provides the foundation for the other concepts we're about to talk about. In particular, the next concept is inheritance. Inheritance is an object-oriented programming language feature and concept that enables systematic reuse of existing method signatures, those APIs we talked about, as well as occasionally method implementations that are defined in what are known as superclasses. They can also be used to reuse fields and data representations as well. For example, the simple tree set is a concrete subclass that inherits and implements the abstract methods that are defined in the simple abstract set superclass. So here you can see that simple tree set is leveraging the interface that's defined, the API that's defined by simple abstract set, and then providing the implementations of those methods. Likewise, simple abstract set implements the iterator method that it inherits from the iterable interface. So you can see that we can have chains of inheritance relationships to provide various features at different levels in the inheritance hierarchy. Third key concept we're going to be covering here is the concept of polymorphism. Polymorphism is a powerful technique that's used to dynamically dispatch methods based on runtime type information. So information that's known at runtime rather than information that's purely known at compile time. This is often known as dynamic dispatching. Dynamic dispatching, or polymorphism, can be used to enhance flexibility, extensibility, and reuse by being able to build upon an existing API and then selectively customize or refine method implementations based on other characteristics that become clear as you go down the inheritance hierarchy. For example, when we take a look at the main driver program for our EX0 case study later, we'll see that there's a factory method called makeSet. And this factory method takes a string, which is the type of concrete object it wants to create, such as a simple hash set or a simple tree set or a simple concurrent hash set. And it creates that object, but it returns it back to the caller as a reference to a simple abstract set, which of course is the superclass. And that allows us to be able to have flexibility to define different implementations by the makeSet factory, but have the code that's using it not know or not care what the specific details of that concrete subclass object are. Therefore, when the add method, or the contains method for that matter, is called on the set reference to simple abstract set, the appropriate implementation of add is actually dispatched at runtime based on the type of the concrete subclass object, for example, simple hash set or simple tree set. And the nice thing about this is it avoids any lexical dependencies on the subclass in the client code that uses that subclass object. So therefore, we could write more generic code that can be reused in more different circumstances and actually extended without having to recompile the program from scratch. Now, this was just a quick recap of some of the key object-oriented concepts and features available in Java. If this seemed very mysterious to you, if you have no knowledge of object-oriented Java, then you may need some more hands-on experience. And if that's the case, I highly recommend you take a look at our freely available MOOC called Java for Android, which you can see at this link. And this is something that was done by myself and some of my colleagues at Vanderbilt University, and could also be a good basis to learn the background that you'll need to be successful when we cover modern Java and its more advanced functional programming features. So that's the end of our overview of key object-oriented concepts and features in Java.